Imagine matching the performance of a 1.6 trillion parameter Goliath on, highly complex enterprise tasks.
Right, but doing it with a model that's, what, less than 1/6 the size?
Exactly, and doing it in a language that isn't English. Welcome to AI Paper Slop. We are skipping the standard pleasantries today because, well, this series is built specifically for you. The machine learning engineers, the AI researchers, the technical practitioners who just need to cut through the noise and stay updated on the absolute frontier.
Yeah, we know you don't have time for fluff.
Right. So today's deep dive into the source material focuses on a technical report that just dropped last week, July 22, 2026. It's the Solar Open 2 paper by the Upstage Solar team.
And honestly, the architectural blueprint in this paper, it's going to fundamentally change how a lot of teams think about scaling compute.
Totally. So we want to give you the 60-second summary right out of the gate. Solar Open 2 is a 250 billion parameter mixture of experts model. It operates with 15 billion active parameters per token.
Which is pretty standard for that size.
Right. But the headline feature is this massive 1 million token context window. And they achieve this using a really novel hybrid attention stack. They interleave standard softmax layers with linear attention layers. And this is the crazy part. They did it using absolutely no positional encoding.
None at all, which we'll get into.
Yeah. And it goes toe-to-toe with DeepSeek V4 Flash and MIMO V2.5 on English benchmarks, and it just completely dominates Korean sovereign tasks.
Oh, absolutely crushes them.
And the Upstage team pulled this off through two massive training efficiencies. First, a 2.3% selective weight transfer from their older model, and second, this wild new pipeline for agentic reinforcement learning called Multi-teacher On-Policy Distillation.
Or MOPD. It's basically a masterclass in stretching a finite compute budget to hit frontier-level capabilities.
Exactly. So the mission for today's deep dive is to dissect the exact mechanics behind these achievements. We're going to look at the math of that hybrid stack, how they avoided catastrophic collapse during the weight transfer, and really break down that RL pipeline. So let's start with the context bottleneck.
Yeah, the 1 million token problem.
Right. Because a whole field is moving toward long horizon agents, right? Models that don't just chat, but actually read massive system logs, plan over hundreds of steps, self-correct. And for that, you need a massive context window.
Right.
But if you try to push 1 million tokens through standard softmax attention, you just hit a brick wall.
You do, because, standard attention scales quadratically, right? Every new token has to compare itself against every single previous token.
Yeah, an n by n matrix.
Yeah, exactly. So when you push that to 1 million tokens, the memory required just to store the key value cache completely explodes, and the raw compute time just becomes, paralyzing.
Right. Serving that in production is just commercially unviable.
Totally unviable. So Upstage bypassed this by moving to a hybrid architecture. Solar Open 2 uses a 48-layer stack, but they totally abandoned the idea of using standard attention everywhere.
Right. They repeat a 1-to-3 pattern, I think.
Yep. 1 softmax attention layer, followed by 3 linear attention layers.
Okay, meaning 25% of the network does the heavy global recall, and 75% does something much more efficient.
Exactly.
Let's look at the softmax layers first. The paper notes they use grouped query attention, GQA, which is pretty standard now, but they added this element-wise sigmoid output gate. Why add another gate right after the scaled dot product attention?
So that solves a very specific training pathology called the attention sink. In standard attention, the softmax operation forces the attention weights across the sequence to sum to 1.
Always 1.
Always. So even if a token doesn't actually need to attend to anything in the past to predict the next word, it is mathematically forced to allocate that attention somewhere. So models learn to just dump all that useless attention onto the first few tokens of a prompt. That's the sink.
Which creates massive activation spikes on those initial tokens.
Right.
And that destabilizes the entire network if you try to push the learning rate too high.
So math totally backs that up. Yeah. So by multiplying the attention output by a query-dependent sigmoid gate, you inject this nonlinearity that allows the model to essentially turn off the attention output for a specific token.
If it doesn't need historical context.
Right, exactly. It makes the output sparsely dependent on the query. And suppressing that artificial sink basically smoothed out their loss landscape, which allowed them to train at a much more aggressive learning rate without the model diverging.
Okay, so that covers the 25%. Now, the paper mentions they used a variation of KDA, or Kimi delta attention, for the remaining 75%, the linear layers. I know linear attention is supposed to solve the memory problem, but how does this specific variant actually compress a million tokens without, losing the plot?
Well, standard attention computes that n by n matrix, which is where the quadratic cost comes from. KDA, and really linear attention generally, just abandons those pairwise comparisons entirely.
Oh.
Instead, it maintains a fixed dimensional recurrent state. So think of it as a tightly packed memory matrix.
Right.
For every new token that arrives, the model computes a delta update and just adds it into that fixed state. Because the state size never grows, the KV cache footprint remains completely constant, whether you are on token number 10 or token number 1 million.
Wow.
So the computation scales strictly linearly.
It's a really brilliant division of labor. The linear layers act as these cheap, highly efficient workhorses just accumulating context, while the sparse softmax layers drop in every fourth layer to ensure the model can still perform like exact needle in a haystack retrieval across that compressed state.
Yeah, it's incredibly efficient.
Okay, let's unpack this because here is the architectural detail that genuinely blew my mind. They removed positional encoding entirely. The no PE revelation. No positional encoding.
Yeah, it completely inverts how we normally think about sequence modeling. The softmax layers in SolarOpen 2 learn no explicit position signal.
Zero. No ropey, no alibi.
None. The relative position of the tokens is carried entirely by the sequential nature of those linear attention layers.
See, I'm trying to visualize how a model understands sequence without being explicitly told where a token sits. Like standard positional embeddings like ropey, they feel a bit like measuring a document with a rigid ruler.
Okay, yeah.
If you train a model on 128K context, your ruler is exactly that long. If you try to measure a 200K context document at inference, the ruler snaps. It physically lacks the embeddings to extrapolate. So how does a linear layer avoid snapping?
That's a great analogy. Think of the linear layer less like a ruler and more like a rolling odometer in a vehicle.
Odometer.
Yeah, because the linear core processes tokens sequentially, right? Incorporating each new token into that running recurrent state one by one, so the token order is encoded intrinsically by the state transitions. The odometer just keeps rolling forward.
It never runs out of numbers.
Exactly. Because there is no fixed length ruler, those extrapolation limits we see with rope just vanish. In principle, this architecture can support an unbounded context length, totally independent of the length distribution it saw during pre-training.
That sounds perfect in theory, but for that odometer to work accurately over 1 million tokens, the paper details a highly technical tweak. They explicitly set a parameter called allow on a gigvol, allow negative eigenvalues to sol.
True.
Yes, crucial detail.
What happens if you leave that set to false, like standard models?
You completely cripple the model's ability to self-correct. In standard linear attention cores, the eigenvalues of the state transition matrix are strictly bounded between 0 and 1.
Okay.
Practically, that means the recurrent state can only do two things. It can persist information or it can decay information.
It can't flip sign.
Exactly. It cannot actively erase. So if the model writes an error into that fixed size state at token 500, it is trapped. The error persists and just compounds all the way to token 1 million.
Wow, so you just drift into noise. Yeah, you cannot solve complex state tracking tasks, like modular counting or parity checks, if your memory can only decay.
So by widening the write strength, allowing negative eigenvalues, and expanding the range from -1 to +1, they essentially give the model a backspace key.
Yes. The state can actively invert and erase previous errors. And because the linear state is the only mechanism carrying token order and long-range dependency across 1 million tokens, that ability to erase is the only thing keeping the long-lived state from degenerating into total noise.
That is just elegant engineering at the inference level. But, solving inference costs doesn't help if you can't afford to train the model in the first place.
Right, which is the real bottleneck.
Pre-training a 250 billion parameter model from scratch costs tens of millions of dollars in compute. But Upstage bypassed this cold start problem using selective weight transfer. They initialized SolarOpen 2 by transplanting 5.69 billion parameters directly from their older, smaller SolarOpen 1 model. That is just 2.3% of the new model's total weights. How do you successfully graft weights from a 102 billion parameter all softmax model into a 250 billion parameter hybrid architecture?
Well, you only take the structural pillars that perfectly align.
Okay.
They kept the vocabulary size identical at 196,608 tokens, which allowed them to cleanly transfer the token embeddings and the final output layers. So the fundamental semantics of the tokens carried over immediately.
Nice.
They also maintained the 48-layer backbone with a hidden dimension of 4,096.
Which means the normalization layers transfer cleanly too.
And that is absolutely critical for early training stability. For the attention mechanisms, they transferred the softmax query, key, value, and output projections because the grouped query attention geometry stayed exactly the same.
Right.
And in the new mixture of experts module, they directly transferred the single shared expert. Everything else is, the linear layer, specific gates, convolutions, the new sigmoid gate we talked about. All of that had to be randomly initialized.
So let's talk about the routed experts, because SolarOpen 1 had 128 experts, and SolarOpen 2 expanded that to 320. If only 2.3% is pre-trained, and the 240+ billion parameters comprising those 320 experts are completely random noise, why doesn't the model just explode? Doesn't the random noise destroy that fragile pre-trained skeleton during the first few gradient steps?
That is the ultimate risk with partial upcycling. You might assume the safest route is to just copy the old 128 experts, duplicate a few of them to fill the 320 slots, get a head start.
Yeah, that seems logical.
But Upstage explicitly chose to randomly initialize all 320 routed experts. If you duplicate pre-trained experts, you risk severe inter-expert similarity. The experts basically collapse into doing the exact same task, and you destroy the specialization that makes routing powerful in the first place.
Oh, I see.
The model survives the random initialization specifically because of the normalization layers and that single shared expert they transferred. The shared expert acts as this massive regularization anchor. It processes every token and keeps the representation stable while the random experts slowly begin to specialize.
The return on investment for this 2.3% transfer is just staggering. For the technical listeners managing their own training runs, the paper notes that reaching a training cross-entropy loss of 1.8 required only 12.6 billion tokens using this selective transfer.
Right.
If they had started from a completely random initialization, it would have taken 21.5 billion tokens. They reached the same baseline capability 1.7 times faster.
And they accelerated that even further with their data curation. They took a massive 20 trillion token pool and aggressively filtered it down to a 10 trillion token pre-training mixture.
Quality over quantity.
Exactly. They used an in-house quality scoring system, heavily optimized the real-to-synthetic data ratio to about 4:6, and pushed math and coding data to occupy more than 15% of the total mix.
Okay, so a smart base model is a great starting point. But the challenge fundamentally shifts when you want that model to act as an agent. Predicting the next word is very different from an agent executing create, update, and delete operations, CUD operations in a live enterprise environment.
Oh, completely different paradigms.
If I tell an agent to update a user's email in a live database, how does the training pipeline actually know if the agent did it safely or if it just, hallucinated a success message?
That lack of source data for safe state mutating actions is a massive bottleneck. You cannot scrape the internet for logs of agents safely deleting enterprise databases.
No, absolutely not.
So Upstage solved this by building synthetic sandboxes and creating what they call a readback verifier.
Readback verifier, yeah.
When the training pipeline has the agent execute a mutation against a live sandbox environment, the system automatically writes a PyTest suite using the environment's read tool.
Oh, wow. So the training system literally runs a script that queries the database to assert the email was actually changed.
Yeah.
And if the PyTest passes, the RL pipeline receives a positive reward.
The success of the readback test suite defines the absolute ground truth for the reinforcement learning phase.
So here's where it gets really interesting for the RL folks listening. Let's talk about the reality of running that RL phase, because reinforcement learning for agents is notoriously brutal on compute. You have a massive cluster of GPUs. Some nodes are assigned purely to generate trajectories, letting the agent interact with tools, make mistakes, navigate those readback verifiers.
And generating a 1,000-step trajectory takes a tremendous amount of time.
Right. And while those generation nodes are slowly unrolling that long trajectory, the other nodes in your cluster are constantly updating the core model policy using shorter finished rollouts, which means by the time your long trajectory finishes generating, the core policy has moved on. The rollout is completely stale. It's off policy.
And standard RL algorithms are ruthless about this. They look at that stale rollout and simply throw it away.
which has to be agonizing for an engineering team. You just burned hours of multi-GPU compute and thousands of dollars in power for absolutely zero gradient update.
Yeah, it's a huge waste. So Upstage implemented this brilliant fix called the Fresh Token Fraction Gateway.
Okay, how does that work?
Well, instead of evaluating the staleness of the entire trajectory as a single unit, the system tracks the exact policy version for every single token generated. They measure staleness at the token level.
Oh, I see. How does that salvage the compute?
If a trajectory meets a minimum freshness threshold, they keep the rollout. For the calculation of a loss, they simply mask out the stale prefix tokens.
Yeah.
The overly stale tokens do not contribute to the gradient, but you salvage the relevant parts of the expensive trajectory instead of tossing the whole thing in the trash.
That is so smart. And the paper mentions they pair this gateway with direct double-sided importance sampling.
Right, because in RL, you calculate a ratio between the probability of an action under the new policy versus the old policy. If the policy has drifted significantly, that ratio can explode, completely wrecking your gradients.
Yeah.
Double-sided importance sampling bounds this ratio on both the upper and lower ends. So if a token's probability ratio falls outside a strictly defined trust region, it is entirely excluded from the update. They are managing policy drift token by token.
Okay, so we now have an agent that can interact with databases and an RL pipeline that doesn't waste GPU hours. But Upstage didn't just train one general agent, they trained 12 separate domain specialists. A coding agent, a math expert, a data analysis specialist. If you take 12 highly specialized models and sequentially fine-tune them back into one single monolithic model, won't the model just overwrite its previous skills?
Yeah, you run straight into catastrophic forgetting, and if you try to combine them using standard supervised fine-tuning, you get severe exposure bias.
Right.
Standard SFT forces the student model to mimic the perfect trajectories of the teachers. But during real-world inference, if the student makes a slight mistake on, say, line 4 of a Python script and drifts into a weird state, it has no idea how to recover because it was never trained on its own mistakes.
It only ever saw perfection.
Which brings us to MOPD, Multi-teacher On-Policy Distillation. How does this actually solve the exposure bias? Upstage used an interactive imitation learning loop. So instead of the teacher providing a static, perfect script, the student model generates the trajectory.
The student drives.
Exactly. The student takes actions, makes slight errors, explores the environment. Then the specific routed teacher for that domain looks at the exact flawed state the student is currently in and provides a target probability distribution for what to do next.
Oh, wow. So the student receives dense token-level supervision over the actual states it visits. It learns how to recover from its own behavior rather than just memorizing an idealized path.
Right. It anchors the student to the teacher's high-performance distribution while remaining firmly grounded in the student's actual operational reality. It is exponentially more sample efficient than providing a sparse reward at the very end of a rollout.
Okay, so we have dissected the hybrid no-P architecture for cheap million token context, the selective weight transfer for efficient pre-training, and the MOPD pipeline for Agentic RL. Let's bring this down to brass tacks for you listening. What does this all mean for actual real-world performance, particularly in the realm of sovereign AI?
The secret weapon here is really the tokenizer. Solar Open 2 inherited the Solar Open 1 tokenizer perfectly. And when evaluated on CoGDPVol, which is their highly rigorous in-house benchmark for Korean office work, Solar Open 2 hits a compression rate of 4.41 bytes per token.
Let's put that in context. It essentially takes fewer tokens to represent the exact same amount of Korean text compared to a global model.
Yes. It packs roughly 24% more information into a single token than the best global model evaluated, which was Minimax M3.
And if you are an ML engineer deploying an application, a 24% boost in tokenizer efficiency is massive.
Oh, it's huge.
It directly translates to 24% cheaper inference costs. Furthermore, it artificially extends your effective context window. A 1 million token window in Solar Open 2 holds significantly more actual Korean text than a 1 million token window in a model trained primarily on English.
And that deep architectural efficiency directly translates to the benchmarks. On English tasks, this 250 billion parameter model competes fiercely with the best sub-320 billion open weights available. It leads MMLU Pro with an 86.2, and it hits a 92.4 on LiveCodeBench.
But the most staggering metric is the jump on that Korean office work benchmark. CoGDP-Vol isn't just some synthetic toy data set. It evaluates real industry deliverables, legal precedents, infection control reports, complex professional documents. The previous generation, SolarOpen 1, scored a 3.4 in this benchmark. It fundamentally could not do the job.
Right.
SolarOpen 2 hit 86.8.
You'd effectively match the performance of DeepSeek V4 Pro.
And DeepSeek V4 Pro is a 1.6 trillion parameter model. SolarOpen 2 matched its performance on sovereign enterprise tasks at less than a sixth of the size.
It provides a definitive proof of concept, a native language specialized model built with domain-specific agentic pipelines and an optimized tokenizer can deliver frontier-scale capabilities at a fraction of the hardware cost. For anyone listening who manages a training budget, the blueprints in this paper, from the fresh token RL gateway to the partial weight upcycling, are immediately applicable methods to stretch your compute.
It's a phenomenal technical achievement, and it leaves us with a truly provocative final thought to mull over. If a 250 billion parameter model can match a 1.6 trillion parameter behemoth simply by optimizing its native tokenizer and utilizing synthetic, culturally grounded training environments. Wait, I shouldn't say it like that. Are we witnessing the end of the era where one massive global model rules everything?
That's the real question.
Yeah. Will the future of AI architecture actually be a federation of hyper-efficient, culturally specific, sovereign models, rather than a single monolithic intelligence burning massive amounts of compute just to understand your local context? It is a paradigm shift worth watching closely. Thank you for joining us for this deep dive into the source material, and we will see you on the next one.